Okay, so we're going to do exercise 21, and then you copy down the problem. So it is an application, or you can say it's a consequence of exercise 18. So mu star is an auto measure induced from the pre-measure. So I'm just going to write down the definition. Is equal to T mu naught of Hj, where Hj is in A, and E is a subset of the union of Hj. Okay, and mu bar is equal to mu star restricted on m star. Okay, and then and then show that mu bar is, so notice that mu bar is a measure on m star. So show mu bar is saturated measure, of course, because it is on m star, because mu bar is a measure on m star. Okay, so we're gonna show that, and then we call the definition for saturated measure. Is say it is saturated even with the equality or hold. So, and then notice that one inclusion is very obvious. As we discussed earlier in one of the exercise that first introduced the saturated measure. And then the second one is what we want to show. So we want to show m star tilde is a subset of m star. Okay, so if we pick E from m star tilde, and then we want to show that E is in star, right? So what I'm doing here is not only to read the problem, but also translate translate the task into an easier one, which is equivalent, while also being equivalent as the original problem. So our goal is to show this, the last line here, right? And then recall what is the definition for E to be mu measurable is for all f in X, mu star of f is equal to mu star of E intersect f plus mu star of E intersect mu star of f intersect E and mu star of f intersect EC. Okay, and notice that this is this is very easy, and for this direction, if the measure mu star of f is equal to infinity, then we're done. So therefore, is suffice to only show. So this is our ultimate goal. Okay, for all f in X with the measure star f is finite, we have the inequality. So I'm going to change this to be larger or equal than. So this is our goal. Okay. So we have f, and f is a subset of x, and f may not be m star measurable. So the application of exercise 18, as I mentioned at the beginning. So by exercise A, what we have is we have by exercise A 18.A, there exists A. So for all epsilon less than 0, there exists A in A sigma, and F is a subset of A, and the measure star of A smaller or equal than measure star of F plus epsilon. Okay, so we have this. And what else do we have? So look at A, right? So A is in A sigma, which is subset of star. So A is A is M star measurable. Since A is an M star measurable, okay, so I'm gonna write it here. Since A is M star measurable, and notice that we assume this is finite and this is finite, therefore this is finite. So mu star of A is finite. By the fact, not a fact, by the assumption that E is mu star delta measurable, we do have that E intersect A using M star. Okay, and why do we want that? Well, so in particular, so if we pick, so particular, we know that A is a sub of X, so that implies mu star of A is equal to mu star of A intersect E intersect A plus mu star of A intersect E, E intersect A C. Okay, so this is equal to mu star of E intersect A plus mu star of EC intersect A. Okay, and then that implies with the previous inequality, we have mu star of F plus epsilon is largely equal to mu star of A, and mu star of A is equal to this, right? And then by monadicity of the measure, because this F is subset of F is a subset of A. Okay, so this is going to be smaller or equal than mu star of E intersect F plus mu star of EC intersect F, and then therefore let epsilon goes to 0. We have mu star of F is smaller or equal than mu star of E intersect F plus mu star of E C intersect F, and then together with the other inequality, we're done, right? So I think the gist for this problem is it is not complicated, but you need to make certain observations, and I didn't successfully make the observation when I was first writing this problem. So one is that so you translate the problem into this, and then you pick that F, and you notice the existence of A, like exercise 18.8, and you need this, and then you also need to apply this, realizing how to use the conditions. Okay.